Hello, everybody. Welcome to Module 8. And this is when we start to tackle something a little bit different. Up until now, of course, last week we talked about missing data, which was a little bit different. We learned about the multiple imputation process. But before that, we were focused mainly on statistical models, mostly regression-based, and also some that had to do with ANOVA or in an ANOVA framework. This week we talk about cluster analysis, and this is actually an algorithm. So this is a process, sort of a recipe that is developed that the computer executes over and over until it sort of arrives at a pre-specified threshold and tells you how many groups you might have, how many latent groups or how many clusters you might have among your data, clusters of people, in this case, because we're in education and social science. So clusters of people based on a series of indicator variables. So this is a really cool and flexible method. I really enjoy it. It just kind of makes sense to me. It's different. It doesn't play by a lot of the same rules as a traditional statistical model. And it takes that sort of intrapersonal perspective where you're really, you're thinking about differences between variables between people. So you're thinking about how people sort of function differently. And it's kind of a cool thing. So let's go ahead and get started. You'll notice there are some new packages we're going to use. Always new packages. Another week, another package in R. So we're going to use the core plot package, which is an easy way to generate some correlation matrices, which are very handy. Tidyverse, we already know. Tidy models is a cousin of the tidyverse. And tidy models is very powerful. It's just starting to be sort of widely used, developed by the same people who developed the tidyverse, RStudio. And it's a way to sort of automate more complex types of analysis and make them easier to understand and visualize and summarize. And so we're going to use it primarily to create some really cool visualizations of our clusters that we created. NBClust is a very cool package that helps you determine the optimal number of clusters. This is a really big question in cluster analysis. How do you know how many clusters is sufficient? Is there any statistical evidence for that choice? Is it purely sort of aesthetics or your own guessing or whatever? So the NBClust adds a little bit of objectivity to that process. The psych package we know already. And then standardize is just a very easy package for standardizing variables. And that is a very common approach. Anytime you do cluster analysis, you usually standardize or z-score your variables before you put them in. All right, so let's run these and get these up and running. And this will take a little bit because there are quite a few packages here that are getting loaded into the system. And as usual, I've pointed my software to the folder that contains the data for this week, just to make it a little bit easier. It's a Stata file, and it's called ELS cluster 500. So this is a random subsample of 500 people from the educational longitudinal study, which is what we used, if you remember, a couple weeks ago when we studied logistic regression. We looked at odds of whether or not a student had an IEP using this large longitudinal data set. Now we're going to look at some profiles of mathematics engagement, also using a subsample of ELS. So let me load that in, and I'm going to call it cluster, like so. There we go, clusters right there. So we have 500 observations of 55 variables. And so now we can start sort of identifying variables we might want to use and looking at them. So the first variable I'm going to look at is SES composite score. Now, I may not actually end up using this one at the very end. It's not going to be a part of my cluster analysis. but it is a variable that would be useful for testing my solution for my cluster analysis. So I want to show it to you. In this week's reading, the Pastor and Ehrbacher chapter, the authors sort of differentiate between internal variables in a cluster analysis and external variables. And internal variables are the ones that we call indicators. They're the things that help us figure out whether or not there are clusters. But once you have the clusters, you kind of have to do something with them. You want to validate whether or not they're meaningful. And that usually means testing whether or not there are differences on an external variable, sometimes called a distal variable, based on which cluster a person was assigned to. And SES is an example of this kind of variable. So I'm looking at profiles of mathematics engagement. We'll learn later what that means. But once I find those clusters, I can then say, okay, do those clusters vary by SES? And so SES serves as an external variable that I can use to validate my solution once I find one. So the reason I put it up front is anytime you do a cluster analysis, if you really want to sort of meaningfully unpack what the clusters are, it's always a good idea to have a set of variables or one variable in reserve that you can then test to see whether or not there are differences, because that adds a lot to the validity of your solution if you can. All right, so let's look at this variable. So I'm going to use the describe function, which comes from the psych package. And I'm going to click here and get a look at this. So this is roughly a standardized continuous variable, SES. Seems kind of strange, right, to do an SES, but ELS has a lot of these composite variables. They basically just pack in information on a lot of different measures. They ask about resources in the home and family income and education. And basically they do a kind of factor analysis and collapse all that into a single composite measure. And having continuous measures is nice for things like control as well. So anyway, the mean of this is basically 0. And the min is -8 and the max is about +2. And just looking at the structure, this is called the socioeconomic status composite version 1. And it does have some negative values, which we haven't recoded yet. That's an important thing. So we would want to recode this if we are going to actually use it, because there are some -8s and -4s. -8 is survey component legitimate skip, and -4 is non-respondent. So I'm glad I did that, because it reminded me of that I should get rid of those -8s and -4s. We can also actually, so the next thing I want to do before I do that, I want to recode all those missing values in this data set. So I'm going to recode all the missings, legitimate skips, partial interviews, and non-respondents to NA. And we used this same process last week. So this should be, by now be fairly familiar. So we are going to, one second, I realized I forgot to start my timer. So I want to know how long I'm yammering on here. There we go. Okay, timer's running. All these little NAF commands do is it recodes all -9s to missing, -8s, -7s, and -4s. And we're doing that in succession using the pipe operator. And then we're going to call this new data set cluster.clean. Cluster.clean right here. Okay. So now I should not have that issue with missing data. We can do a glimpse. This is the same set of 50 variables from a couple weeks ago, so I'm not going to spend a ton of time going into it. But we shouldn't see any -9s, -8s, -7s, or -4s. We see, for example, a -2 or a -3 in here. That's fine. I'm assuming those are legitimate values, but the others are more like survey values that we want to get rid of. And we can look at a histogram now of that SES variable now that we've gotten rid of the composite score. And so this would be a great example. I talk a lot about, I've talked before to you, our folks, about how you don't always want to use geom histogram unless you have a truly continuous variable. And this SES variable is truly continuous. And so it is a great fit for the histogram plot. And you can see it's nicely sort of normally distributed, or at least symmetric, going roughly from about -2 to +2, with higher scores suggesting people with higher levels of SES. I also showed a couple other options here. So you can put an outline around your bars here with the color command. That's pretty fun. So that just gives it a black line around the outside. And then fill, of course, you can play with this. There's a list. If you just Google ggplot color names, you can change this to any color. So this is steel blue. I don't know. I had a student a couple years back who found this color and ended up using it. So I started using it too. But lots of fun things you can do to customize. Okay, so now let's start looking at the variables we're actually going to use in our cluster analysis. And so this is roughly thinking about this. I want to understand profiles of math, learning, maybe engagement, although I know my ed psych folks will probably say that not all of these indicators are true indicators of engagement. So this is probably like a multi-dimensional profile of math learning. And so the first thing I'm going to use is this question about how many hours the student spends on homework per week. So this is some sort of a measure of like time put in, effort, out of school work, things like that. So let's use the describe and structure commands here to get a look at this. So BY here just means base year. So this was as collected in the first year of the survey. So these students were sophomores. So this is the base year hours per week spent on homework, both in and out of school, So this is kind of like a measure of effort in a way, how many hours the student is spending working on that. Here's some sample values, the structure command. Here's the describe function. So the mean here is 12. So on average, student spends about 12 hours a week on homework. A little less than an hour or 2 hours a day, which seems about right. We do have some missingness, n equals 439. We have a min of 0, a max of 98. So wow, some folks are really spending a lot of time on homework. I want to look at that. Skewness is high, and kurtosis as well. So might actually want to get a look at this. So the next one down is just a ggplot to get a measure of what this looks like. So, descriptives don't always tell us everything. Aha. And when I do this, sure enough, I've got some outliers in the mix here. So most people are spending between 0 and 35 or 40 hours. And then there's basically nothing. And then I have a small cluster of folks around 100. For purposes of a cluster analysis, it actually does make sense to have your variables at least symmetric. They need to be continuous, or at least functionally continuous, but it does make sense that they are close to normally distributed. And so I'm probably, when push comes to shove, I'm probably going to filter these people out, and I'm going to show you how to do that. Now, that's not a decision you take lightly, right? And you have to, of course, describe that in your analytic plan and justify why. But these people are so far above the distribution for everybody else that it's likely to probably throw things off a little bit. Notice here, this is now John Bar, because we're now measuring in discrete hour measures instead of a truly continuous measure. And this is forest green, so we can track the colors as we go across. All right, so that's hours spent on homework, and I'm making a mental note. I gotta address that. Then we have math engagement, and so it's basically the question is something like, actually, I think the question is in here. So let's run our. This is a nice little combination of things you can run here. So describe gives you descriptive statistics, table gives you a breakdown of values, and structure gives you the labels. So you can run all three of those. And so describe, mean of this thing is 2.5, and it goes from 1 to 4. It's basically a Likert scale-ish item. Goes from 1 to 4. The STEM gets totally absorbed in mathematics. So this is the extent to which the student gets totally absorbed in mathematics. For higher numbers are like often, one is lower numbers are not as often. So higher numbers mean higher levels of engagement, mathematics engagement. So that's good to know. We can do a plot of this. This is in dark red. Give you a look at engagement. So most people are sort of in the middle, right? Towards the lower part of the middle. That seems about right for math engagement. I don't know that a lot of people are always really engaged in math or any subject for that matter. So that seems about right. So that's my second variable. So I've got hours of homework, I've got math engagement, and then my third variable, oops, jump back here. There we go, is math importance. So same thing, I'm going to describe it, get a table for it, and look at the structure. Math importance again is a 1 to 4. The mean is again about 2.5. Very close actually to the one above, which is interesting. I'm actually double checking to see that it is BY87F though. That's the name of the variable. And okay, mathematics is important to me. Is the question. Higher numbers suggest agreement. Lower numbers suggest a lack of agreement. And we throw this in a plot. There we go. And again, it looks about right with this very similar distribution with most folks at a 2 out of 4, and also quite a few folks at a 3 out of 4. All right, so just to recap, I've run through my external variable that I want to use, which is SES. That's going to be the variable that I'm going to use to validate my solution. Now I've run through, I've recoded all my missing values, since this is a big longitudinal data set with survey values in it, -9s, -8s. All those have been coded to NA. And I've gotten descriptive statistics, labeling, and graphs for all of my indicator variables, which are hours spent on homework, math engagement, and math importance. So I am in pretty good shape. Now I need to do a few more little things here before I really start to do the work of the cluster analysis. And cluster analysis is very particular about the types of data that you can use. And so it's important to just be aware of that. So the first thing you need to do is you need to standardize all of your variables. So we want to standardize those. And then we want to also get rid of those folks who are at less than 50, or sorry, more than 50 homework hours. And I'm actually going to change this. This will be different in yours. I'm going to filter first, and then I'm going to do that, and then do this. Okay. So first thing I'm going to do is I'm going to take this cluster.clean, and I'm just going to rewrite it. So I'm going to start with cluster.clean, and I'm going to filter out, or filter in, the filter function in R actually filters in versus filters out. So filter in everyone who has a base year homework less than 50. So that gets rid of all those people. There weren't that many. I think there were 10 or 12 at the end that had more than nearly 100 hours of homework per week. So I'm going to filter those folks out. And then I'm going to add standardized versions of homework importance and engagement, which are going to be my indicators. And I'm going to do that using the mutate function, our handy mutate function. And the command is just called scale. And that comes from the standardize package. So if you just run this scale and then the name of the variable, and you do need to list the actual data set first. It's not sort of tidy in that sense. But as long as you list all those things, then you are going to get standardized versions, z-scored versions of all 3 of these measures, which is great. And that'll allow us to put those into the cluster analysis. Oh, let's see. Homework can't be recycled. Input is scale. Standard is clean. Ah, yes. Okay, that's why, I learned a lesson here. That's why I put it at the end. I do need to put this at the end so it can, otherwise the sample sizes don't match up. Sorry, very, very riveting here, but I do want to show you, I go through the same stuff with our mistakes. I'm just a little more used to them and a little more comfortable with what happens when they do. Okay, so now I've got that all filtered, and notice cluster.clean now only has 425 observations instead of 500. And those 75 observations are those people who were way on the high end of the distribution. So now cluster.clean is fully standardized. We can run the describe function on each of these things. Hopefully the mean is pretty close to 0. It is, yep, which is great. And the standard deviations of all these things should be pretty close to 1, and they are pretty close. Homework is a little off, I think, because of the people were left in for the standardization, but for our purposes right now, we can keep that the way it is. We have roughly standardized variables. Okay, so now the last thing I'm going to do before I actually conduct the cluster analysis is to do a little correlation of my 3 indicators. And I think I showed you last week, you can do core.test in base R is a nice thing. The only thing with core test is it only gives you 1 correlation at a time. And sometimes it's nice to get a matrix of all the correlations. And so this, this core plot library here package will help you do that. So the first thing you need to do is you need to winnow down your data set to just the variables you're going to use for your cluster analysis. And so that's what we do here. And we're going to call that data set core. So that's a very important thing to keep track of. So core is the original cluster.clean data set. And we've selected only the 3 indicators we're going to use. And then we've eliminated all missing values using this NA omit function. So this is an important point. Cluster analysis cannot handle missing data. So it is not, I know we just learned about multiple imputation, which is super cool. But unfortunately, cluster analysis is not that flexible. It cannot handle missing data. Now, there are some new developments statistically, actually just a package I read about the other day that handles multiple imputation and cluster analysis in R. So this is an area of active development, but for the time being, there are not good solutions for handling missing data. You might be able to do something like impute the median value for missingness, but that's probably about it. So for our purposes, we're just going to exclude any missingness. So first, let's run that. So first load in the core plot package, and then create this new data set called core, and that's up here. So notice we drop down to 333 observations. So there's quite a few large amount of missingness here. And we only have 3 variables, which are our 3 standardized variables. And then to get the cluster, to get the correlation matrix, the command is just core. So we're going to run core on core. So COR on our new data frame called core. And I just called it core cluster. You actually don't even have to call anything if you don't want, but that just saves it for later. So now we have a correlation matrix, and here are the correlations between our indicator variables. And hopefully you do see some correlations between these things. For example, math importance and engagement are very highly correlated at 0.5, and engagement and time spent on homework are actually negatively correlated, which is kind of interesting, at -0.16. So that's kind of interesting, engagement in math and in homework. Homework is not terribly correlated with math importance at about minus 0.08. So if you have more indicators or more continuous variables, you can throw them all in here and get a bigger correlation matrix if you need to. All right, so this is probably a good stopping point. So just to recap what we've covered here, we started by inputting our ELS 500 data set and recoding all those missing values. Then we glimpsed it. Then we took a look at a histogram of our external variable, which is SES. Then we looked at our internal variables, hours spent on homework. We found that there was this little bump of people with very large hours spent on homework, engagement in math, and math importance. And then we shrunk our, we standardized our variables. That's very important. You have to z-score your variables using the scale function that was up here. We filtered out those people with really high homework values. And then we ran we pulled just the variables down into a separate data set and then did a correlation of just with that data set. So now we're ready. We have 3 numeric variables all in one data set, and we're ready to actually do the cluster analysis, which I will tackle in part 2 of this video. So hopefully that's made sense, and I will see you soon.